Fantastic.
Well, it's preparing to go live.
Yeah, there's always this little delay, but then it starts earlier.
Perfect.
Good. Great. Well, welcome to Neuroccino, everyone, on this Monday morning, the 4th of April. The way it works is everyone is welcome to present a paper, a book chapter, YouTube video, any piece of science that you got excited about, and we just discuss it to the best of our knowledge. The only rule is that you don't present your own work, but someone else's exciting work. And that's it. Just let us know, come and present. Now, today we have Hervé present.
Yes.
And Ahmed is here as well. Do you have a paper for us as well, Ahmed?
I could present something now if you want. Yeah.
Great. Okay, so we have a double bill today. Hervé, do you want to go first? But bear in mind that there's a second paper today.
I'm happy to do it another time if you want to take more, because I know it's a 30-minute block, so I'm happy to do it another day, by the way. Yeah, absolutely fine.
Okay, thanks.
Okay, so let me share my screen. Okay.
And share the link, please, in the chat.
Yes, okay. And I didn't prepare that. Okay, let me find. So it's a Nature paper, so it's easy to find it. Brainwide. Okay. So the title is Reproducible Brainwide Association Studies Requires thousands of individuals. So let me share this link here, and here you are somewhere. Okay, the chat. Yes. Here you go. Can you see the screen? Yes, everything is okay. Yeah. Okay. So I picked up this article because it made quite some noise recently in the neuroimaging community. So why? It's because it's talking about the reproducibility, and we know that we are in we are still in the reproducibility crisis in the scientific world, and specifically in the neuroimaging field. This paper remind me about, for the oldest of us, the Voodoo paper. I don't know if you remember this Voodoo paper that was about the double dipping, where you select your brain. So double dipping means you do twice your neuroimaging analysis. So you focus your results, and you kind of biased it. Okay, so we are back to that with this paper because so it's talking about the neuroimaging studies, and we know that neuroimaging studies were pretty good at working on brain structure and function. So that means looking at mapping, associating structure and function. And that provided us a window to study mental health and cognition in general. But the people that started these kind of studies discovered that it was not so simple because you need to deal with a lot of variability and inter-individual differences. And I would like to show you, and I think it's good. So there was so Scott Marek, which is who is the first author of this paper, so started a trade on it, and I think the first comment he made on this paper is pretty important. So this paper is not about all neuroimaging, but very specifically about cross-sectional correlations between individual differences in brain structure and function with psychological phenotypes. Please read and share with appropriate nuance. I think that this last sentence is really important. So you want to emphasize that is about association studies and not about mapping functions. And it's why when we go back to this, the title, they use this term brain-wide association studies. So, and if we use the acronym, it's BWAS, and that reminds us about the GWAS analysis, which is genome-wide association studies. And it's interesting they do this analogy because in the imaging genetic field, 10 years ago, or even more now, we had this crisis or this problem of using candidate gene, where you select your a very specific gene or polymorphism, and that was the first studies about trying to combine genetic and imaging, and we found out that it was very difficult to reproduce all these results. And so after that, so the studies about genetic and imaging started to increase to use a GWAS analysis. So that means collecting a lot of subjects, more than 1,000, to have robust results. So after this introduction, so this paper is looking at the question of this paper is looking at the sample size when you do BWAS studies. So it's a big paper, a lot of results and methods. So I will walk through it and try to summarize it. So for that, they use the EBCD datasets, which is a large dataset of subjects, around 10,000, 10 years old, and they picked up the structural and functional imaging. What they did, so they collected these phenotypes. So looking at for example, the cortical thickness, and for the functional, they look at the resting state functional connectivity. And they use different cognitive and psychological measure. So the first thing they look at, so they look at the correlation, the association between these cognitive and mental health questionnaires and the imaging phenotypes. So here's one of the main figure. So here on the left, you have everything about the structure, and on the right about the function. So they collected all the phenotypes. That means for the functional, they use the age, the component, the network. And for the structure, they use the vertex, the region of interest, and the network. As you can see, when they look at the cognitive ability or the psychopathology, which are two different cognitive scores, they found correlations, but the R score is very low. So I think the median is 0.01 in general. And even if they take the top 1%, they got only 0.06, so very low correlation. Here is the regions that are where the correlations are significant. But the most interesting is the third row, where you can see that the R, the correlation, the score, they play with the sample size, and they so they increase the sample size starting from 25 until 2000. And so you can see you have a decrease of, the more you increase your sample size, the more you decrease your confidence interval. So that works for all of so for the structural and the functional, and for the cognitive ability and the psychopathology score. And that is an example of what you can find when you use very small sample. So the last row, so this is 25 subjects selected randomly. So you can just by chance to have opposite correlation. So, and they find that for all the, so for structural, functional, and for the two different scores. So that means it's yeah, you cannot trust results with less or around 25 subjects studies. So they try to replicate on different data sets. So ABCD is a multi-site. So I think they have 10 sites. And so they picked up the UK Biobank and the HTP, and they found, again, they look at the same kind of correlation, and they found that the score was kind of similar using this different data set. After that, they look at the kind of error you will find in this kind of BWAS studies, and when you use very small sample. So they look at for example, the false negative errors. So here so they increase. So they did bootstrapping, and they increase progressively the sample size, and they play also with the p-value. So selecting a very stringent p-value or a very lenient p-value. So what is interesting is that you need to increase a lot your sample size to get less false negative errors. But you can see that even if you increase more than 1,000, you still have a lot of false negative, high false negative rate. And what is interesting, and maybe we will discuss it, is that the more stringent is your threshold, the more you increase this false negative error. So they look at the inflation. This is how much you overestimate your correlation based on the sample size, and so you need to increase your sample size to decrease your inflation rate. That is so I showed you just before when you get opposite results. That is again to get less percentage of opposite results. You need to increase your threshold, your sample. Statistical power is the inverse of false negative, and probability. So that is the really depressing message. The probability of replication. You can see here that to replicate your results, you need to at least go over 1,000, and even at this number, if you have a very stringent threshold, your chance of replicate your result will be very low. So it's better to get a more lenient threshold to get a replication study to work. What is interesting, and that is the positive aspect, and they don't discuss it a lot, is the false positive. So that means when you have a results, when you get results, you are pretty sure that if they are significant, they are true. Okay, so that was the idea. So that was based on univariate correlation between one phenotype and one score. So they look after that to the multivariate approaches. So using machine learning and stuff like that. So here they look at support vector regression and canonical correlation analysis. So just trying to explain these methods. So oftenly when you do these, you need to train your model. So you use a training sample, so which is a training sample, and you can try to replicate what your model found out in another sample. So you can use an in sample. That means you use the same subjects that you use for your training sample, but the best is to use an out sample, out of sample. So that means you select, you pick other subjects out of your training sample to test your model. So this is the kind of figure you can get. So the in sample here is here on this axis, and the out of sample here. So as you can see, when you look at the model using an in sample, you are often you will find something significant because you use the same subjects. But to find that your model is working well with an out of sample, it's more complicated. And so here the color scale show you the number of subjects in your sample. So the more you increase, the more chance you will get significant results. So the significance is represented by this dashed gray line. And when you go over 200, for example, in this case, so that is for structural imaging and cognitive ability, if you get around 200 subjects for the out of sample, you will get something kind of robust. So the same representation here, on the left, you have the cortical thickness, and on the right, you have the resting state functional cognitivity phenotypes, cognitive ability, and psychopathology. So this part is about the support vector regression, and this part is about the canonical correlation analysis. So kind of similar. So to summarize what this figure showed you is that first, if you look at the two kind of phenotypes, the functional seems to be better at looking at finding association, so on the right part, and it seems that cognitive ability or cognitive scores are kind of better at it's better to use cognitive scores to find associations. So when you look at the difference between green and purple. And last thing, no, and that is the same thing. So you see that the blue is better than the yellow, which is the functional, and here you see that cognition scores are better than psychopathology scores. Okay, so I think there is no other figures, and just the conclusion was about, so they say that when you do association studies, it's better to use a large number, but the take-home message is that also that they don't say you don't have to use small samples. They say just that small samples are more fit to mapping when you want to associate structure and function, or when you do lesions, or even longitudinal studies. When you have small sample but you follow them through time, it will be good. It will be good even if you have a small sample. But when you want to do association study, it's better to have a large study. And just to come back to Twitter, there is a nice thread about this paper, but he's an author in the paper, and he made this distinction between where is it? I think it's here, between association or what is say association, yes, and detection. So task fMRI will be very good in detection even with a small sample, and again association is something else. Nice thread also by Nico Dusenbach. If you want to, is trying to summarize all what I said. I use a lot of what he is describing in his thread. Tomasio also, and also just to make some kind of, so this thread or this paper was used in by a lot of neuroimaging guys. So for example, Paul Thompson made a thread about the Enigma consortium. So it's a consortium that tried to collect a lot of subjects together. So, and I found, just to conclude, these. So I know some people are using tractography, and so this guy, Frank E, I think, was saying that is it also the case for tract-wide association studies, the TWAS. Okay, so I think I will finish on that here, and if you have questions, I'm ready for it.
Amazing, thank you very much. I was looking forward to someone presenting this paper, so I'm very glad we now have it in our list. Are there questions? Okay, let's start with Ma.
Hello.
Hello.
Thank you for the presentation. It was really interesting. So one thing that this paper made me think, maybe I'm wrong, but is like when you have a big sample, it's less probable that you find some results because you lose the individual variability. And so at the end, you just capture what is really common for a huge sample of persons. So in your opinion, what do you think would be like the best approach for the future? To use these super big samples and capture only which is really common and we can generalize? Or we start studying individual variability in a more precise way than we are doing right now, like because we can know now that this is really important, like individual variability is present, and maybe it's even more interesting than the common things, given there are many, maybe few. So I don't know, what do you think?
No, it's really yeah. This is the biggest question of this paper, and I'm glad you asked it. I think 2 points he made, or 1 point the authors made in the article is saying that okay, so you need a large number, but also, or you can do also something else, is to refine your neuroimaging. So they talk about methodology, but that means also just to reduce this inter-individual variability. And I think something maybe they didn't discuss enough is that here they use cognitive score that are very general, and maybe there is something to do here also to focus on what you are looking at. And I think one thing, so to answer your question is we had. So this discussion is going on since a long time, but this paper is kind to stabilize it. But I think there is this discussion about stratifying the population also, because you select a big sample with a large variability. So maybe it's good also to focus on these samples and to select. And what you saw in this paper is that for example, for mental health, it's pretty bad because, for example, schizophrenia or depression, we know that not all the patients are the same. So you need to refine these, as you say, these inter-individual variability to focus on what you are looking at. So because if you select all the depressive patients, you will find nothing, because you will find just the common thing which is not real in this kind of patients. So yes, I think we need to work on that. And that the problem of this paper, I think, is it's not a problem, but the issue is that if we look at it, say, okay, so we cannot do neuroimaging anymore, because if I need 1,000 subjects, how can I do it? Except if I use ABCD, UK Biobank, but I will not be able to answer all the questions. So I think we need to be very careful saying that, yeah, it's good to have a large number and we can do that, but it's also good to use small sample to study very focused and to have focused questions.
Yeah, thank you.
Thank you very much. Also, you probably guessed, but Ahmed kindly said he's going to present another time to give us more discussion time for this paper. Sorry, Michelle has a question.
Thank you, Ave. We've seen that paper, and of course we cannot all acquire 1,000 subjects to do our research. But I was wondering, and it's true for the false negative, but as far as you don't reject and say those regions are not involved because they're not significant, which is another statement of frequency stats, you find. But you can take for example, smaller sample, let's say 20 subjects, and replicate it in another sample of 20 subjects, and then if you're able to replicate your findings, that you should be in the fair, no? What do you think?
Yeah, but yeah, so what I think they wanted to make these so when they in the figure 1, as you can see, you have 2 different samples of 25 and two different results. So I don't know if with 25 and 20, so.
But if you have 20 and 20, you have the same results. Would the likeliness of this to happen is much higher.
Yeah, for sure.
But it's much lower. So that means that you're closer to
patients. Yeah, but what they try to say that even if you have the same results here, yeah, you cannot be completely sure. I don't know.
You never can be sure.
Yeah.
Until you scan them all.
Oh yeah.
Another question. So I have another question. It's like they use those different population, but they didn't look at like you might have differences in the brain works and association between the brain and function. According to the country you're from, the ethnic or the cultural background that you have, and this is not taken into consideration here.
Yeah, I think they have. So in the paper, they say that they try to cover out some of these effects, but they say they did it and didn't change a lot of things. I think it's in the supplement. In the supplemental materials. So I think that was a question from the reviewers, something like that, because yeah, they added that, and I think it's really a good question, because again, the variability between population and ABCD is 10 years old. UK Biobank is around 50 years old subject. So they did this figure saying that they're replicating the R score in general, but it's true that I'm pretty sure the confidence interval and the errors you do with different populations and the variability you add to your associations is based on that. So you need to.
I kind of join like what Ma has been saying. It's like it's either the method is really, really bad, and that's why we need that many subjects, or there is really something that we didn't take into consideration in the way people can solve or associate to a given function that brain differently, and that's it looks like we're missing something.
Just to jump in there's also a question/comment in the chat here that taps into the same train of thought, and it says, I wonder if the study highlights also that psychopathology is less fit to be studied via the association approach. Maybe it's more difficult to define, quantify a psychopathological trait. Thus, it might not be a problem of sample size, but rather the fact that we're approaching the study of psychopathologies as cognitive abilities.
Agreed completely. Yeah.
But that was from Valentina as well. And that has been a sorry, I'm losing my voice. That has been a recurring theme in our discussions, that the way we define cognitive abilities and also cluster people based on them into pathological groups or groups of interest may actually have its limitations. So, yeah. Leah.
Yes, thank you. So I was trying to get some direction from this paper. So it seems that more than 25 like number of subjects is a good number for replicability. And I was also wondering if they have comment about R values and P values, how we should interpret the results, if they touch this point of discussion about the statistics.
You say 25, the number of subjects?
Yeah, you show like a graph where they say that above 20, yeah, there was 25. You said that higher than that they...
No, you should get around 1,000 subjects.
Yeah, but at some point, like all the graphs start from 25 because you comment that that is the number that you need as like the lowest number, right?
Yes, it's the lowest number they use. This and they use this number because in OpenNeuro they say that the mean sample the mean subject sample is around 23. So in OpenNeuro, all the functional imaging study or all the neuroimaging study you will find is around, the mean is around 23. So they started with this.
Okay, there was not a statistical reason. Okay.
Okay, and after they say that, yeah, you need to get over 1,000 to get something which, but there is not a clear threshold in their graph. They're just saying that, yeah, you need to get a large number. 1,000 it seems to be the minimum.
Okay. So
and,
okay.
Yeah, you were saying about the so they play with a statistical threshold. And what is interesting here, that one of the main results is that if you, and it's kind of counterintuitive in the way that if you want, here you see that the more you increase your sample size, the less you will get false negative error. But if you use a very stringent threshold, so the green one, you will miss a lot of stuff. So it's better when you have a large number, or what they say, it's, or maybe not better, but you will find less false negative errors when you use a more lenient threshold, which is completely counterintuitive of what we are thinking, because we do a multiple comparison correction to correct for it, and so that is interesting.
Okay. Okay, thank you.
I mean, we do the multiple comparison and everything to reduce the p-value threshold, because the idea is, of course, if we reduce the p-value threshold, we will increase the false positive rate. But
yeah, exactly.
We want to reduce also the false positive rate. And this is the ratio, I think, between the two that we have to take it into account. And I think it's lacking that we don't have like a ratio in here to show, okay, here, if you take this kind of p-value with this kind of number subject, you'll get this ratio of false positive over false negatives, which would be interesting to have, and they don't show it.
Yeah.
Yeah, I was trying to have some like directions for future studies with the big numbers of subjects. Yeah, to this discussion. But yeah, thank you.
So what's the conclusion in the end? Do we all have to now go for big samples? Can we still do our small samples? Are we giving up on brain associations? Where is this taking us?
No, but the problem is it's a Nature paper. And yeah, see, if you look at it, someone from outside this field will say, okay, neuroimaging, if I see a number below 1,000, it's crap. And it's not. So I think, yeah, so as I said in their trade and in the paper, they discuss it's not that. So we need, you can continue to do small samples, but for example, for what we are doing, so for example, brain mapping, longitudinal studies, stuff like that, and for association studies, you need to be very careful when you find an association. That is the take-home message. But we need to be careful that other people use this paper to say that, yeah, neuroimaging is not good. So this is always the problem when you try to summarize a message. We need to be very careful that we not throw away everything in the way.
Yeah, I agree. I think from the outside, it looks like we're deconstructing our own discipline with a series of papers.
That's how it looks like. But still, I think I'm like a Nature group journal are really pushing for that. If you have a replication in your study of your findings, it's still a big statistical demonstration that there is a real effect. You still have one chance in billions that you have like two groups that by chance shows the same association that does not exist in anybody else. But it is very much slow. Very much lower than like if you do an association like and you don't replicate it. So we have very less chance of false positives. But still, I think there might be something behind that we're not tackling correctly in terms of brain phenotypes and the relationship with function.
And on that cheery note, that's all the time we have. Well, thank you so much for picking up this paper, Hervé.
Thank you, Hervé.
Thanks for the discussion, and lovely to see you all. We see you again next Monday, 9:30 sharp. And we'll see who's presenting next week after we push the double bill today. We're going to work it out. So do join us next Monday morning for a new discussion. And until then, have an exciting week in science. Bye.
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 Victor, if you